Hi, Mr. Luong. So for part A, to draw the free body diagram, I'm going to draw the big M first. So this is M, and then this is FG for M, and then FN. Oh, it should look a bit more equal with FG. So it should look about the same. Yeah, that's the same. And then for small m, it's going to be right here. And then like F, and then there's also T for this one, for the M, big M. And for the small m, there's FG of M. And then there's T. And T should look less than the FG because you're accelerating downward. So the vector accelerating downward should be greater than T for it to have acceleration going down. And then for part B, I have to derive an expression for acceleration. So I know that mg minus t equals ma, and then t equals big ma. So I substitute in for t, solve for a, so then a would be mg over big M plus small m. And then for part C, I have to derive an expression for tension. So then I know that, let's do it over here. C, I know mg minus ma equals t. So then I just solve for t. Oh wait, that is it. Yeah, that's it for t. And then part D, so for part D, I'm going to use this equation to prove it. So when you increase the mass, the tension will increase as well because it's directly proportional. But let's say when you divide the m to both sides to get acceleration, increasing the mass will decrease the value at the top. So increasing the mass will decrease acceleration because your m is in the denominator. And it also shows like the inverse relationship between a and m. As you increase the m, a would decrease. For part E, I have to derive an expression for the system in terms of m, big M, mu, k, and g. Okay. So I know T minus Fk equals big MA. And I also know that Fg or Mg minus T equals to MA. And then I'm going to solve for T. Plug this T into the other equation. Expand Fk into mu k Mg Ma. And then I'm going to get acceleration to the other side. Take out the A. And then divide both sides by that to get acceleration equals to mg minus mu k big Mg over m plus m. Okay, for part G, wait, yeah, for part F, sorry. So for part F, I'm going to use this equation right here. T equals mg minus ma. Or actually, sorry. It asks for terms of mu k2, so I'm going to use that equation. So T equals to ma plus fk. Plug in the a I got for last time. And plus fk. Oh. Plus fk is mu kmg. Yeah, for part F. And then for part G, the tension will increase. Tension will increase because you need more tension to overcome the friction pulling the big M back. So for it to have the similar acceleration, you need a bigger force to overcome the friction to have the same acceleration. Okay, for part H, I have to draw a free body diagram for all the forces acting on each block. Okay, part H. For big M, big M right here, Fn and Fg should both look almost the same, or they should look equal. And then there's Fk. Oh, there's Fk. And then there's also the contact force from the M. So it's like F, M to big M. And then you also have tension. So tension should be greater than all the forces. Here, let me draw a bit bigger. Yeah, it should be like bigger than what both of the Fk and F, the contact force from M, added up together because you're accelerating to the right. And then for the small m, there's Fg of m, Fn of m, and there's also the contact force from big M. And then for the hanging block M, it's going to look like Fg is greater, and then T should, wait, I have to draw the same T before. So it's about like the same, oops, sorry. The other T should look like this, and the Fg should look way bigger because you're accelerating downward. Okay, for part I, to calculate for the acceleration of the system, I'm going to write my equations first. Oh wait, sorry. For I just realized something. For this F, this the M that's like the small m on the surface, there's also Fk acting on it. So the Fk should look somehow about like this much. Yeah, because that block is still accelerating forward too, so the Fk holding it back is going to be smaller than the contact force pushing it. Okay, equals 2a, and I'm going to substitute T in, and then expand Fkm to 0.8 times 2g. And then I'm going to do some side work for Fm of m. Oh, and the reason why I founded the contact force for the big M to small m is because the magnitude is the same for both of them. So solving for one of them will get me the answer for the other one because they're both the same. So then I'm gonna substitute what I got for this to that equation right there. Let me move this down a bit. Okay. And then you got 3a plus 0.8. Oh, this is supposed to be multiplication. Equals to 2a. And then I moved 3a to the other side to get 8 times 2 times 98, 3.5. Wait, let me just solve for all the values. Okay, 29.4 subtract 3.528 subtract. Oh wait, yeah, there's also this 3a over here, so there's 6a in total on this side. So I'm gonna add 6a to the other side. Yeah. So it's just 0.18 times 3g is going to be 5.292 equals to 8a. And then A should come out to be about 2.58 meters per second square. I mean 2.57 meters per second square. Part J, I'm just going to use the equation I did here to solve for T. T should be equal to 50. Oh, sorry, hold on. It should be equal to like about 21.68 newtons. And then for the contact force, I'm going to use the equation I found here. And then the answer should be around 13.01 newtons. And then for part L, Since acceleration is constant and it starts at rest, I think it'd be easiest to use common form and to AH. Bf squared is 0, so then Bf equals rad to AH, rad to 2.57, H20. Bf should be around 10.14 meters per second. And then for part M, I'm going to use the Vf equals minus Vi over A equals T. And then since Vi is 0, you just do 10.14 divided by acceleration 2.57 equals T. T should be like 3.94 second. Okay, for part for part N, I'm going to sketch out the graphs, what the graphs look like. Let me draw that a bit better. So this is x of t, and this is t. Oh, let me just do x, and then the units for this is going to be meters. T is going to be seconds. It should look somewhere around like a quadratic. Okay. And then it looks like this because it starts at 0. So then right there, the slope of that is a horizontal tangent, which means it's 0 velocity, initial velocity. And then it's going to be quadratic because the acceleration is constant. So yes. Now this is B, which is going to be meters per second. And then this is T, which is going to be seconds. So B is just going to be like a derivative of the graph of x, and just going to be like a straight line. And Vi right there is 0. And then it's going to grow at a constant rate because acceleration is constant. So then A of t, A is going to be meters per second square, and then t second. And t is going to be a straight line because acceleration, like I said before, is constant. And net force is going to be newtons, and T is going to be second. And then, okay, so net force T, the graph for this one is going to look like constant 2, because net force equals to ma, and then since m is constant and a is constant, that means everything about net force is constant.